So in today's and tomorrow, probably tomorrow's session also, we'll be discussing on the concept of design of combined footing. So this is again another type of footing that we most commonly used, especially in the scenarios get changed when we use this combined footing. So let's understand where we use this combined footing, and then I'll talk about the design procedure, and then with the problem statement. Suppose let's say we have the isolated footings. Isolated footings are nothing but you have only one column which is attached with one footing. Okay, if you see it from the top view, this is how it looks like. If you see it from an elevation point of view or elevation view, so this is how it looks like. This is called as an isolated footing. So the isolated footings can have the rectangle shape or they can also have the square shape. So that's about isolated footings. Now coming to the combined footing. So combined footing is nothing but you will have, or we will have only one footing or one foundation slab, and on the top of one foundation slab we'll have two footings or two columns, not footings, two columns will be there. They can be a square column, they can be a rectangular columns, whatever the type. So if you see it from the elevation point of view, they goes or they look in this way. So this is how the isolated combined footing looks like. So when you have columns more than one, especially we use this combined footing for two columns. So when we have to make two columns on the same foundation slab, such kind of footing is called as combined footing. So for this one, this is column one and this is column two. For both column one and column two, we have the same footing. So that's why we are going to call it as combined footing. Now the question is where we need this combined footing. Okay, that's one important parameter. Suppose let's assume that we have a site area. Let's consider this is our site area. And along this side, road is available. And along all the four sides, the neighbor buildings are available. I'll just make it as B. So buildings are available. So some existing buildings are available. But now you want to construct your own building in your plot. So this is your site area, or this is your plot area. Now, what's the simple thumb rule? The thumb rule is like one footing should be there on each corner of the plot or on each corner of the site area. So that's one thing. This we know. And there should be other footings that should be available based upon the size of the plot area. Suppose let's say apart from these four columns or these four footings on all the four sides, let me keep a couple of columns or a couple of footings at the center of the sections as well. Let's say this is another one and this is another one. Somewhere here can be another one and somewhere here can be another one. So these are the internal footings or internal columns, you can say. So these are the external columns, or you can call it as major columns or major footings, the corner ones, and the pink color ones are the blue color ones are the internal columns. Now, in some cases, there are situations where the phenomena or where the requirement of a load transfer will be in this way. Suppose let's assume that you have arranged the columns in this way. So there are total 9 columns are available in this site. Now you need one extra column, or you need to provide one extra column along with the footing somewhere in this portion. Let's say I need to provide one extra column at this portion. Okay, at this portion. Now assume that all the 9 columns, excluding this one, all the 9 columns are isolated footings. Now, when you are providing this column, this additional column, you are designing the isolated footing. But when you are designing the isolated footing, what actually the problem was, the footing which is available for this column, okay, the footing which is available for this column is going in this way. And the footing which is available for this column, the black color column, is going in this way. So what is happening here? The footing of this column, the blue column, is getting coincided with the footing of the black column. So here there is no chance of providing the isolated footings. You cannot provide isolated footings in this way. Why we cannot provide isolated footings? Because the footing of this particular column is getting coincided with the footing of this column. So since these footings are getting coincided with each other, the load distribution will not happen in a proper way. So to avoid this kind of phenomena, what we can do is instead of providing two individual isolated footings for these two columns, what I will do is I will provide a common footing for these two columns. Okay, I'll provide a common footing for these two columns. And then this I'll call it as a combined footing. So usually the combined footings will come into picture when you have two columns close to each other. Okay, when the columns are close to each other, or when footings of the columns are getting coincided with each other, in such cases, you cannot provide the isolated footings. So the only option that we have is we need to provide the combined footing. Okay, we need to provide the combined footing. Now, what is the advantage of providing combined footing? The advantage of providing combined footing is, suppose, let's say you are providing only the isolated footings. Okay, isolated footing for this one. Okay, this one is having an isolated footing, and the black column is also having one isolated footing. So if you provide two isolated footings for these two columns, what is happening? One thing is the footings of these two columns are getting coincided with each other. This portion will have huge amount of load distribution compared to this portion as well as this portion. So when this portion is experiencing huge amount of load distribution, if it is strong enough, then it will restricts the load, or it will react the load. But when this portion of the footing is not strong enough, then both the portions of the footings will get collapsed. So when the footings, when partial portion of the footings is getting collapsed, obviously it will have an impact on the columns as well. Okay, it will have an impact on the columns as well. So now the idea for this one is to provide the combined footing. Okay, the idea for this one is to provide the combined footing. So one idea of providing combined footing is to save the, or is to ensure the load distribution to happen in a proper way. That's one idea. The other idea is, when you look into economical aspects as well, you are going to save to huge amount of cost for the construction. Now here I'm just considering only one combined footing. Now let's say you have some 20 columns that are available in your site. Out of these 20 columns, at least 8 columns are experiencing this kind of things. So 8 column, instead of providing 8 isolated footings, what I'll do, I'll provide only 4 combined footings. Two footings, I mean, for 2 columns, I'll provide 1 footing. So I can reduce the cost of construction as well. So that way, this combined footing will be helpful. So that's the simple concept of usage of combined footing. So the only rule of usage of combined footing is, the first rule is, when two isolated columns are getting coincided with each other in such a way that the footings of those two columns are getting coincided, then load distribution will not happen properly. So to ensure the proper load distribution, or to ensure uniform load distribution or pressure distribution, you have to provide the combined footing. That's one scenario. The second scenario is when two columns, or when one of the column is close to the boundary lines and the other column is very close to that boundary line columns. In such cases also, we have to provide the combined footings. These are the only two scenarios where we use combined footings, right? So now let us understand one problem statement, and then we'll try to solve a problem on how to design a combined footing. So let me show you the problem statement. I hope you are able to see the problem statement. So you can see this is the problem statement as two columns having a cross section of 250 by 250 mm and 300 by 300 mm, loaded with 300 kilonewtons and 500 kilonewtons respectively. And the center to center distance between the column is 4 meters. Okay, the center to center distance between the two columns is 4 meters, and the bearing capacity of soil is 100 kilonewtons per square meter. And there is one limitation that is provided: design a rectangular combined footing being width as 1.5 meters. So the width is limited, the footing width is limited to 1.5 meters. Length you can provide as much as you can, but the width of the footing. So what is meant by width of the footing? Width of the footing is nothing but, suppose, let's say if this is your plan view. Okay, so this length, the length of the footing can be as much as you want, but the width of the footing, that is B value, is limited to 1.5 meters. That's the limitation that they have provided. That's one thing, right? And the grade of concrete is M20 and the grade of steel is Fe415. So how many columns are there? Two columns are there available. Both are square columns only, 250 by 250 and 300 by 300. And one column is carrying a load of 300 kilonewtons and another column is carrying a load of 500 kilonewtons. And the center to center distance between two columns is 4 meters. Okay, right. You can see the figure here. If you see this combined footing, So one column is having 300 kilonewtons of load and another column is having 500 kilonewtons of load. And if you see it from the plan view, this is how they looks like. And the center to center distance between the two columns is 4 meters. That is what they have provided in the question. The center to center distance between the column is 4 meters. So by maintaining 4 meters center to center distance, we have to provide or we have to design the columns in such a way that the width of the footing is limited to 1.5 meters only. Length you can provide as much as you want, but width of the footing is limited to 1.5 meters. And also the center to center distance between the two columns is also limited to 4 meters. Okay, it is also limited to 4 meters. And both columns are carrying some amount of load. Again, they are not equal amount of load or equal capacities of load. Different loads are being carried. One is 300 kilonewtons and the other one is 500 kilonewtons. So for this, we have to design the combined footing. Now, while designing the combined footings, the process of designing gets changed. I mean, the formulas, those things will remain same. But in the design of combined footings, we have to be very careful in calculating the shear force and bending moment diagrams. Our shear force and bending moment calculations are very much important in the design of combined footings. That's what we are going to look after. I'll clearly explain how to go with the calculation of shear force and bending moment once after we go through certain process. Right. Just give me a second. Yes, thanks for your wait. So the first thing that we are going to do is we have to design the loads or we have to find out the loads. So what are the loads that are coming onto the structure or that are coming onto the soil? So there are two loads. One is 300 kilonewtons of load and the other one is 500 kilonewtons of load. So let's look for the calculation of loads initially. So the first step is the calculation of loads. Okay, the first step is the calculation of loads. Now, what are the two loads that are coming onto the columns? One is 300 kilonewtons and the other one is 500 kilonewtons. So total load, okay, total load coming from columns. Okay, total load coming from columns that equals to 300 kilonewtons is from one column and 500 kilonewtons is from another column. So a total of 800 kilonewtons is coming onto the foundation slab or is coming onto the soil, you can say. Right. So how to get the self weight of footing? So self weight of footing equals to self weight of footing equals to 10% of column load. That factor will not get changed. While designing any type of footing, the self weight of footing is taken as 10% of column load. What is column load value? 800 kilonewtons. So that equals to 80 kilonewtons. So therefore, total load coming onto the soil or total load transferred, the total load transferred to the soil equals to 800 kilonewtons plus 80 kilonewtons. That gives us 880 kilonewtons of load is the total amount of load that gets transferred to the soil. So based on the load calculation, we can determine the dimensions of the footings. That's the second thing. So how to determine the dimensions of the footings? So let me write that dimensions of the footing. So there is one limitation that is given. The width of the footing is limited to 1.5 meters, I guess. Yeah, the width of the footing is limited to 1.5 meters. That is what is given in the question, right? So in order to find out the dimensions of the footings, what we have to solve is first we have to find out area of the footing. So that's the first thing. Required area of footing equals to. So how to find out the required area of footing? Area capital A equals to, I'll just make it as AREQ. That is area required. Area required equals to load by SBC of soil. Okay, what is load? Load is 880 kilonewtons, the total load transferred to the soil, divided by SBC of soil. What is SBC of soil? It is 100 kilonewtons per square meter. So load by SBC of soil is 100 kilonewtons. That equals to 8.8 square meters. So this is the load, this is the area of the footing that we have to provide. Now, which type of footing we have to provide? Is it the rectangular footing or the circular or the square footing? It is given in the question that design a rectangular combined footing. Now, suppose here it is provided in the question itself or in the problem statement itself, but what if in the real-time scenarios? In the real-time scenarios, most of the times, or 99.9% of the times, whenever we design the combined footing, we provide, or in real-time scenarios, engineers will provide only the rectangular footing, not the square footing. Okay, especially when you are providing the combined footings, it is always suggested to provide the shape of rectangle than the square, even though the columns are square columns. Okay, even though the columns are square columns, it is suggested to provide the rectangular footings irrespective of what type of column we have. Whether it is a square column, circular column, or a rectangular column, it is advised to provide the rectangular footing, especially for the combined footing design. Right. So required area of footing is 8.8 square meters. So from this, we have to decide the length and width of the footing. Okay, from this, we have to decide the length and width of the footing. But here, there is one limitation that is given in the question. What is that limitation? The width of footing. Okay, the width of footing is limited to, okay, the width of footing is limited to 1.5 meters. That is what given in the question. So let me write here, the width of the footing is limited to 1.5 meters. I'll call this as B suffix F, that is width of footing. So you know the width of footing. From this, you can easily find out the length of the footing. You know the area equals to LF into BF. Okay, length of the footing into the width of the footing. So we know the length of the width of the footing and the area. So from this, you can calculate the length of the footing. So length of the footing, you will be getting it as 6 meters. Okay, if you round it off the value, you will be getting the value of length of footing as 6 meters. So therefore, okay, therefore, provided area of a footing, okay, provided area of footing equals to, what is width of the footing? 1.5 into the length of the footing is 6 meters. So 1.5 into 6 will give us 9 square meters. So what is the area that we have to provide? Area we have to provide is 8.8 square meters. And how much we have provided? It is 9 square meters. So there won't be any problem with this. Right. So now we have to find out the one factor which is called as center of gravity. Why we need to find out the center of gravity? That we need to understand first. So the first thing that we need to understand for this is, let me write that center of CG of load. CG of, I'll just keep this heading CG of load. You can keep any heading, whatever that is convenient for you accordingly. Right. So what is this CG of load? Suppose in order to have the uniform pressure distribution, okay, to have the uniform pressure distribution, the CG of load, that is center of gravity of load, should coincide with, okay, should coincide with the center of gravity of footing. Okay, the CG of load should coincide with center of gravity of footing. Why it should coincide? Because in order to have the uniform pressure distribution. So this thing is a new thing when you compare with the design of isolated rectangular footing and isolated square footing. In those two design considerations, we did not consider, or we did not bother much about the center of gravity. So here we need to bother about the center of gravity of load should coincide with the center of gravity of footing. Why this is happening, or why we need to consider this? Suppose if you observe this particular column, two different columns are available. Okay, two different columns are available. And if you see the properties of these two columns, each column is having a different dimension. So one column is having a dimension of 250 by 250, and another column is having a dimension of 300 by 300. That is one difference. And the second difference is both columns are not carrying equal amount of loads. So the first column is carrying 300 kilonewtons of load, and second column is carrying 500 kilonewtons of load. So what is happening here? There is no pressure distribution. I mean, from this we can say that pressure distribution will not happen uniformly. So that means eccentrically distributed or eccentrically pressure distribution will happen. It will not happen exactly at the center. Axially powered pressure distribution will not happen. It will happen eccentrically pressure distribution. So if you have eccentrically pressure distribution, or if you have eccentrically load distribution, what will happen? Suppose since this column, the second column, this one is carrying huge amount of load, obviously this portion of the column or this portion of the footing will experience more bending than this portion of the column or this portion of the footing. So what will happen for this? Since the settlement will happen more in along this side than when you compare along this side, the footing will tend to fail. So in order to have the uniform pressure distribution, we should be very careful in identifying the center of gravity of the section. Okay, it is important to identify the center of gravity of the section. Now the question is where the center of gravity of the section will be available. So let us assume that the center of gravity is available at some distance or at some point along x. Okay, let's say what I'll consider is I am going to consider from this column. Let me call this as a column 1 and this as column 2. From the center of the column 1 to some point at the center, the center of gravity will be lying. And this distance, I'll call it as x. Okay, this distance, I'll call it as x. Right? I hope it is clear. So let me explain you one more time. So what I am telling here is, suppose if you are designing, let me keep it here. Yeah. So suppose if you are designing the two columns, okay, let me have the footing and I have two columns here. This is the first column and this is the second column. So the center to center distance between both the columns is 4 meters. Now what I need the center of gravity. Why I need to find out the center of gravity? Because these two columns are having unequal amount of load and the dimensions of these two columns are also not same. So since the properties are not homogeneous, the pressure distribution will not happen uniformly. So to ensure uniform pressure distribution, what should happen? The center of gravity of the loads, okay, the center of gravity of the loads and the center of gravity of the footing should coincide with each other. Okay, the center of gravity of the loads and center of gravity of the footing should coincide with each other. Why it should coincide? When the center of gravity of the loads and the center of gravity of the footing should if coinciding with each other, then there won't be any non-uniform pressure distribution. Okay, there will be uniform pressure distribution when you ensure the center of gravity of loads to be combined with center of gravity of the footing. Now here what I am considering is, so center of gravity for these two columns, okay, center of gravity for these two columns will lie somewhere here only, in between these two columns. It will not be lying anywhere other sides. It will be lying in between these two columns only. So what I am considering is I am calling this as a column 1 and this as a column 2. Okay, this was column 1 and column 2. Now here what I am doing is I am considering a center of gravity or CG point at a distance x from center of the column 1. Okay, from center of the column 1, I am considering the center of gravity of will be lying at a distance x from center of column 1. You can also consider the center of gravity point from center of column 2 also. That's completely up to you. There is no problem with that. Okay, but any one point you have to consider. That's mandatory. Right. So once we consider the distance as x, that is center of gravity point, from this we have to find out the value of x. Okay, from this we have to find out the value of x. Now here, one thing which we need to understand is we know the center to center distance between the two columns. What is the center to center distance between two columns? It is provided in the question, which is 4 meters. Okay, it is provided in the problem statement itself. The center to center distance between the two columns is 4 meters. Right. This is one thing. And the other thing is from the center of this column, okay, from the center of the column 2 to the extreme edge of the footing, I'll consider this distance as B. Okay, I'll consider this distance as B. And also from the center of column 1, okay, from the center of column 1 to the extreme edge of other side of the footing, I'll consider this distance as A. Okay, I'll consider this distance as A. Understand these things, it is very important. So the center of gravity point I'm considering at a distance called X. Okay, from the center to center distance between the columns is already given in the problem statement, which is 4 meters. And from center of the column 1 to the edge of the footing or to the nearest edge of the footing, I am considering the distance as A. And from center of the column 2 to the nearest edge of the footing, I am considering as the distance as B. Right? Now, what will be this distance? Okay, what will be this distance? So we know the total distance is 4 meters and this distance is x meters and this one will become 4 minus x meters. Okay, this distance will become 4 minus x meters. So now our intention is to find out the value of x. Okay, once we find out the value of x, then we can get to know the values of A and the value of B as well. So that makes it easy to identify the center of gravity of the section. Right. So now let's identify the value of x, which is the center of gravity of the section. Okay, which is the center of gravity of the section. Right. So let me have that figure. I already have drawn that figure. Yeah. So this is the figure that I am talking about. Right. So this is the figure. Okay, you can see clearly I'm considering a distance center of gravity point. So at a distance of x from the center of the column. Any column, it can be the column 1 or it can be from column 2, but I'm considering it from the left column. And the center to center distance between these two columns is 4 meters. And then the distance from center of column 1 to the nearest edge of the footing is A, and the center of column 2 to the nearest edge is distance as capital B, right? And this distance is 4 minus x. Why it is 4 minus x? Because the center to center distance between these two columns is 4 meters. So since this is x meters, 4 minus x meters. So let's calculate the value of x now. So in order to calculate the value of x, so x equals to, so 500 into 4. What is 500? 500 is, I'm just calculating the moment. Okay, from this column, from column 2, what is the load that is coming? From column 2, the load that is coming is 500 kilonewtons. If you see here, so from column 2, the load is 500 kilonewtons. So 500 into 4, okay, 500 into 4, force into perpendicular distance. Okay, 500 into 4 divided by the total load. What is total load? 300 from the column 1 and 500 from column 2. So if you solve this one, you're going to get the distance of x, which is 2.5 meters. Okay, the value of x is 2.5 meters. It is very important to calculate this distance called x, especially when you are designing the combined footings. In our other types of footings, it's not required, but here it is important. Right. So now let's calculate the projection length, that is capital A and capital B. So let me call it as projection length, projection of footing, projection of footing on left hand side from the center of column 1. Okay, from the center of column 1. So I'll call it as C1. Right. That equals to, that is capital A. Capital A equals to, what is this distance? L by 2. Okay, the total length is LF. So from center, it is LF by 2 and LF by 2. So what I need this distance, that is capital A distance. So half of the total length of the footing, that is LF by 2 minus X, will give us this distance. Okay, half of the total length of the footing minus X will give us the distance of capital A. We already know the value of X, that is 2.5 meters. So A equals to L by 2, okay, L by 2 minus capital X. Okay, L by 2 minus capital X. What is L? That is length of the footing. What is length of the footing? Length of the footing is 6 meters that we have already found out. Okay, the length of the footing is 6 meters. So 6 by 2 minus X value. What is X? 2.5 meters. Okay, 2.5 meters. So 6 by 2 is 3. 3 minus 2.5 is 0.5 meters. That is the value of A. Similarly, the value of B also we have to find out. That is projection of footing on right hand side from the center of column 2. So I'll call this as a C2, so which is capital B equals to. So how to find out this distance, capital B distance? We know the total distance is LF. So LF by 2, okay, LF by 2 minus 4 minus X. Okay, LF by 2 minus 4 minus X will give us this particular distance. I hope it is clear. So if you have any doubts, please unmute and ask the doubts. So LF by 2, that is L by 2 minus, okay, L by 2 minus 4 minus X distance, 4 minus X. So what is L by 2? L by 2, L is length of the footing, that is 6 by 2 minus 4 minus X. 4 minus, what is X value? That is 2.5 meters. So if you solve this one, you're going to get the distance as 1.5 meters. So that's the distances of capital A, which is 0.5 meters, and capital B, which is 1.5 meters. So from this, we have to calculate the upward soil pressure. Okay, upward soil pressure, W equals to, how to calculate the upward soil pressure? Total load, that is 800 kilonewtons, divided by area of the footing, that is provided area of the footing, which is 9 square meters. You can see here. Total load is this one. Okay, so total load from the columns divided by the area of the footing. So 800 divided by 9, that gives us 88.89 kilonewtons per square meter. So that's the upward soil pressure. So once we find out the upward soil pressure, now the next thing is we have to find out the moment or depth required for flexure. Okay, the depth required for flexure. So how to find out the depth required for flexure? We have the formula mu limit equals to 0.138 FCK BD square. That's the formula that we have. Okay, BD square. So this is the formula we have. But do we know the moment value here or ultimate moment value? No. So the first thing is we have to find out the ultimate moment. In the design of rectangular and square footings, we have found out the mu value in a different way. But here, since we have the two columns, okay, since we have the two columns with two different intensities of loads, you can consider this as a simply supported beam with two loads. Let me draw that one. So suppose if I have to consider, let's say this is one beam, okay, a simply supported beam, you can say. So this is one support and this is another support. And on the top of beam, we have two intensities of load. So this is column 1, okay, and this is column 2. So I'll call this as column 1 and column 2. So column 1 is having an intensity of 300 kilonewtons and column 2 is having an intensity of 500 kilometers, right? So we know the distances also. This distance is capital A, this distance is capital B, and this distance is X. Sorry, is this X? No, it is not X. It is the center to center distance between two columns, which is 4 meters. And the total length, that is length of the footing. This also we know, right? So from this, we have to find out the shear force and bending moments. So shear force at each point and bending moment at each point. So what I'll call is, I'll name the points. So I'll call this as point A. Okay, I'll call this as point A, and this one as point B, and this one as point C, and this one as point D. So at each of these points, we have to find out the shear forces and we have to find out the bending moments. But here, when you are finding out the shear forces and bending moments, one thing which we have to remember, especially while calculating the shear forces, at each point, that is at A, B, C, and D, at each point, we have to find the shear forces along the left side of the point and also along the right side of the point. That means, so shear force at A along the left side. Okay, shear force at A along left side, shear force at B along the right side. So like this, we have to, sorry, shear force at A right side. So at each point, we have to find out two shear forces. Why it is required? Because the intensities of loads are getting changed. So whatever the load that is available along this side may not be the same intensity of load along this side. And whatever the load that is available along this side may not be the same intensity of load along this side. So for this reason, what we have to do is we have to find out the shear forces on either sides of each point. Okay, either sides of each point we have to find out. Right. So I hope it is clear. Right. So let me have that figure. I have already drawn that figure. Yeah. So this is the figure that I was talking about. So the next thing is we have to find out the moments. Okay, shear force. Let me, what is the step number? Step 4. Shear force and bending moments. Okay, so from this, we have to find out the shear force and bending moment values. So how to find out this one? So this calculation is very much important here. So please have a focus on this one. So let me draw the figure here. Right. So I hope you understood this figure. So you can see I'll just try to shorten it. Yeah. So you can see here. So column 1 is having a load of 300 kilonewtons and it is at a distance of 0.5 meters from the left side of the footing. And column 2 is having an intensity of load as 500 kilonewtons and it is at a distance of 1.5 meters from the right side of the footing. And the center to center distance between the two columns is 4 meters. Up to here it is fine. And the total length of the footing also we know it is LF value. And we also know the upward soil pressure, which is 88.89 kilonewtons per square meter. So while calculating the shear forces and bending moments, it is important to consider the upward soil pressure also, because that is also one type of load. Whether it is acting from the top or from the bottom, it is a load only. Right. So shear forces, as I was mentioning, shear forces shall be calculated at left and right sides of each point. Okay, shear forces shall be calculated at left and right sides of each point. And here the point, this one, okay, this one and this one. These two are the column points. Okay, these two are column points. So let me write that one. So I'll call this as point A. Let me write it in with another color. Yeah. So I'll call this as a point A. Okay, this as a point B, and this as point C, and this as point D. Okay, so we have to find out the shear forces at all these points, right? So now let us find out the shear forces value. So before finding out the shear forces value, let us find out the pressure value in kilonewtons per square meter. So usually we have the pressure value in terms of kilonewtons per square meter. So let us find out the value in terms of kilonewtons per meter. Okay, so while calculating the loads, we should not have the area loads. We should have the point load. Okay, so let us do that. So we need to convert the pressure, that is area load, into point load. So we need to convert from kilonewtons per square meter to kilonewtons per meter. So how to convert that? So in order to convert that, we have a simple calculation, that is total pressure. Okay, that is 88.89 into the distance. So you can consider either this distance or this distance, that is either 1.5 or 0.5. It is always better to calculate the maximum distance. So I'll just make it as 88.89 into 1.5. Okay, so that equals to 133.34 kilonewtons per meter. So this calculation we can clearly see in the software also. I'll show you that once when we are doing this. Okay, so this is how we can convert the area load into the point load, especially the pressure value. Right. So now let's calculate the shear force and bending moment. So we have the shear force and bending moment values at A, B, C, and D. Right. So first, let me keep the heading as shear forces. So as I was mentioning, shear forces at each points we have to find out. So shear force at A, that is, I'll make it as left side of A. So do we have any load on the left side of A? No, there is no load that is available. So therefore, 0. And similarly, shear force at A on the right side, that equals to 0 as well. Okay, that equals to 0 as well. Right. Now let us find out shear force at B. Okay, shear force at B along the left side. Right. So how to find out the shear force at B along the left side? So you can see the upward soil pressure is available, which is 133.34 kilonewtons per meter. Okay, because we have converted, we should not take this 88.89. That's an area load. We should always consider the point load only. Right. So 133.34 into what is the load here along the left side of this point B. So 133.34 is the pressure, upward soil pressure, into this distance. Okay, I'm considering it from the left side. Okay, I'm calculating the shear forces from left side to right side. So 133.34 into 0.5, that is distance. So that's the shear force value, 133.34 into 0.5. So that equals to 66.67 kilonewtons. That's the shear force at B on the left side. Now we have to find out the shear force at B on the right side. Can somebody tell me what will be the value of shear force at B along the right side by seeing this calculation and this particular figure? Can anybody guess? It's okay, even if it goes wrong also, but just give it a try, because you all know that strength of material structural analysis basics. Can anybody let me know what will be the shear force at B on the right side? Instead of value, you can just tell the calculations. Anybody? Can anybody guess? It's okay even if it goes wrong also. Let us have a conversation, that's it. So nobody wants to give a try. Right. So shear force at B on the right side. Let me write that. Shear force at B on right side. So at right side, what are the forces that are available? So at right side, the forces that are available are, so you have the load that is coming, okay, that is 300 kilonewtons. You can also consider this load along this side also, but I'm just considering along the right side. Okay, the load on column 1, that is 300 kilonewtons. So 66.67. Okay, 66.67, that is previous load, minus, I'm considering all the upward forces as positive and all the downward forces as negative. Okay, upward forces as positive and downward forces as negative. So what is the downward force here? 300 kilonewtons. Since 300 kilonewtons is acting downwards, I'll consider it as negative. That's why minus symbol, minus 300. So that equals to, you'll be getting the value in terms of negatives, that is 233.33 kilonewtons. Okay, 233.33 kilonewtons. That is the shear force at B on the right side. Right. So similarly, let us calculate the shear force at C along left side. Okay, shear force at C along left side. Can anybody tell what is the shear force at C along the left side? Previous value, that is previous load, that is minus 233.33 kilonewtons, and anything else that is available. So we have the upward soil pressure, which is of intensity 133.34, which is acting at a distance of this one, 4 meters. Okay, shear force at left side of C. So this entire load, which is acting at a distance of 4 meters, and the previous load. So minus 233.33 plus 133.34 into the intensity of load, at which distance this load is acting, 4 meters. So into 4. So that gives us the total load, which is in terms of positives, that is 300 kilonewtons. That's the shear force at C along the left side. Similarly, shear force at C along the right side. Okay, the previous load, which is 300 kilonewtons, and what load is acting along the right side of column 2? 500 kilonewtons. Is it a upward load or a downward load? It's a downward load. So I said that upward loads are considered as positive and downward loads are considered as negative. So since 500 is acting along the downward direction, it will be 300 minus 500. That will give us minus 200 kilonewtons of load. That's the shear force at C along the right side. Right. Now, let us find out the shear force at D along the left side. So what is the shear force at D along the left side? This is point D. So the previous load is minus 200 kilonewtons. Okay, minus 200. And what other loads are available at point D? We have the pressure, upward soil pressure, that is 133.34, which is acting at a distance of 1.5 meters. Okay, with 133.34 is acting at a positive direction or negative direction. Upward forces are positive, so it's a positive, that is plus 133.34 into the distance, which is 1.5 meters. So it will be equals to 0. Okay, I think it will be 0 only. Yeah, it will be 0 only. Right. So that's how we can find out the shear forces at all points. I hope it is clear. If you have any doubts, you can unmute and ask the doubts, or you can also refer the recorded video once I upload it into the YouTube. Right. So that's the point here. Now, what we have to do is we have to draw the shear force and bending moment diagram. That's the critical part here. Okay, right. So let us draw the shear force and bending moment diagram. Initially, I'll just show you roughly, and then I'll show you how to make it in a proper way. So here you can see the shear force at A. Okay, at A is 0 both along left side and right side. Now here you may ask, what is the shear force value at D along the right side? Right side, obviously there are no loads. So shear force at D along the right side, there are no loads, so that will be 0 only. So there won't be any problem, right? So shear force at A is 0 and B is also 0. So the point starts here like this. So let me draw with blue color. So this is the point. Okay, it is 0 load, and shear force at B is 66.67. So upwards is, upward I'm considering it as positive, and downward I'm considering it as negative. Okay, so 66.67 is positive. So up to point B. So suppose let's say this is 66.67. Okay, this is 66.67, and then shear force at B along the right side, which is 233.33 in a negative direction. So you should come down, and somewhere here it will be 233.33. So at B, we have the one load which is at positive, and we have another load which is at negative, right? And then shear force at C along left side, it is 300 kilonewtons. Let's say the 300 kilonewtons is somewhere here. Okay, 300 kilonewtons. Now we have to join these 2 points. Okay, we have to join these 2 points. So that's a shear force at C along the left side, and along the right side. Okay, it is minus 300, minus 200 or 300. Yeah, minus 200. Okay, so along the point right side of C, we have minus 200. Suppose let's say I'll go minus 200 somewhere here. Okay, this is minus 2, and shear force at D is 0. This is how the shear force diagram will looks like. Okay, now here one shear force diagram is okay, it's very easy and we have drawn that. But here one thing which we have to focus is this particular point. At this point, what is happening? The bending moment, the shear force value is changing its sign from negative to positive. It is changing. Can anybody tell me what is this point called as? When the shear forces or bending moment changes its sign, what is this point called as? Anybody? Anybody remembers what is that point called as?
Point of contraflexion.
Point of contraflexion, which is POC. So this point we have to find out. Okay, at what distance this point of contraflexion is acting? That's the point of contraflexion. So we have to find out the point of contraflexion, which is available in between the two columns, that is point B and point C. So that's where we are going to look into the factor of point of contraflexion. So if you don't, or if we don't calculate the point of contraflexion, what will happen? So we don't know where we have to provide the maximum reinforcement. See, you know along this side, along the downward side, you have huge amounts of forces, negative forces. But you don't know up to what distance the reinforcement has to provide. Here I have just mentioned it as one particular point. But what is the distance of this particular point so that I can provide the reinforcement effectively? So in order to find out the length of the reinforcement that has to be provided effectively, we need to find out the distance of point of contraflexion. The distance of point of contraflexion. Right. So let me take that diagram. I have already drawn that. So let me just copy and paste it. Yeah, this is the diagram. Let me just paste it here. Only with, sorry, it is getting copied. The other one I need. Right. So let me crop it only with the shear force values. Right. So here you can see this is the point of contraflexion. So this distance we have to find out now. Okay, this distance we have to find out. So here what I'll do is I will assume the point of contraflexion is at a distance x1 from the center of column 1. Okay, this distance I am going to assume it as this particular distance. I am going to assume it as x1 from center of column 1. You can also assume this distance as well. There is no problem. But it's completely up to you. From which side you want to consider, that's totally your choice. But here what I'll do is I'm just assuming it from this side. Give me a second. Yeah. So the point of contraflexion, let's assume the point of contraflexion is at a distance of x1. Any notation you can give. Here I'm just giving it as x1. At a distance of x1 from the center of column 1. So that is basically C1, you can say, from the center of column 1. So now we need to find out this particular distance. So the remaining distance, whatever that is there on the right side, I'll call this as 4 minus x1. So the total distance between these two columns is 4 meters. So if I consider this as x1, what will be this distance? What will be this distance? This will be 4 minus x1. So this will be 4 minus x1. It's not clear, but consider that. I'll write it, however, in the later case. Right. So now let us find out the distance x1 from the center of the column 1. Right. So what is this total? What is the total load on column 1? 300 kilonewtons. So 300 divided by 4 minus x1. Okay, 300 divided by 4 minus x1. So 4 minus x1. Okay, that equals to, I hope you understand this calculation. 300 divided by 4 minus x1. What is 300? 300 is the load that is coming from the column 1, equals to, what is the shear force at B value? At B, it is 233.34. Okay, shear force here is 233.33, and the load that is coming onto the column is 300 kilonewtons. So 233.34, 233.34 divided by x1. 233.34 divided by x1. So I'm just doing the calculations for these 2 points. What are they? This one and this one, the top one. This 233 and 300, 300 kilonewtons. So I'm just calculating the x1 distance, right? So now let us work with the value of x1. So if you solve this one, you're going to get the value of x1 that is equals to, so I'll just directly write that x1 equals to 1.75 meters. So if you solve this equation, you are going to get the value of x1, which is at a distance of 1.75 meters. That's the point of contraflexure value. So that is the distance from left side of the column. Similarly, if you want to find out from the right side of the column, so the distance from the other side of column equals to 0.5, which is the distance. Okay, this distance from here to here, that is the distance, which is 0.5 meters, plus the point of contraflexure value, which is 1.75 meters. So that equals to 2.25 meters. So that's how we can calculate the shear force value. Okay, this is the entire calculation with respect to shear force. So you try to understand this one. It's very important, and it's also equally complicated as well, because we have different intensities of load and different dimensions, all those things. Right. So the next thing is we have to find out the bending moments. So how to calculate the bending moment? Similarly, bending moments also has to be calculated at each point, A, B, C, D as well. Okay, at each point we have to calculate the bending moment, and maximum bending moment also we have to calculate. And we know that the bending moments at coordinates, that is MA equals to MD equals to. So the bending moments at each sides of the section or each sides of the beam, whatever that is. So at each sides, the bending moments will be 0. So MA equals to MD equals to 0. Now let's find out the bending moment at B. Okay, the bending moment value at D. So how to find out the bending moment at D? Force into perpendicular distance. So at B is this one. Okay, the point B is this one. Let me write it here. So this is point B, and this is point C. This is D, and this is A. So bending moment at ends of the section will always be 0. So MB. So here we have the upward soil pressure. Okay, we have the upward soil pressure. So what is the upward soil pressure value? 133.34. So we have converted into point load. So 133.34 into perpendicular distance. So that is 0.5 square. Okay, 0.5 square divided by 2. So what is 0.5 square? That is distance from B to A. Okay, this distance from B to A. WL square by 2. That's a simple formula. Okay, so if you solve this one, you are going to get the value in terms of value as 16.0 667 kilonewtons meter. So since it's a positive value, it's a sagging moment. Okay, we know this sagging and hogging moment. If it is in negative, it's a hogging moment. If it's a positive, it's a sagging moment. So I'll just make it as sagging. Right. Similarly, moment at C. So moment at C equals to, how to calculate the moment at C? Moment at C equals to force into perpendicular distance. Again, the same formula only. That is force into perpendicular distance. So 133.34, which is the pressure intensity, into the perpendicular distance. What is perpendicular distance from C to D? So the distance from C to D is 1.5 meters. So into 1.5 square divided by 2. Same WL square by 2 formula concept. So from this, we can calculate the moment at C as well, which will be 150 kilonewtons meter. So this is also a sagging moment. Why? Because the value is in positive, right? So from this, we have to calculate the maximum bending moment as well. So how to calculate the maximum bending moment? So here, if you again draw the bending moment diagram, so the moment at A and D is 0. So I'll just show you that diagram instead of directly writing that one. So this is the bending moment diagram. Let me crop it. Right. Forget about this value, that is 187.49. So that we have to find it out now. So here you can see the bending moment at A is 0 and bending moment at B is 16.667. That is positive. So positive bending moments always has to be represented along the downside. Negative bending moments always has to be represented along the upper side of the neutral axis, you can say. So 16.667 and 150 at point C, at point D it is 0. So this is how it goes. Okay, now we have to find out this bending moment, that is maximum bending moment at point of contraflexion. So at point E, we have to find out. So we have found out A, B, C, and D. So let us find out the bending moment at point of contraflexion. So I'll just make it as POC, that is point of contraflexion, or you can also give it as point E as well. Any name you can give some notation. So bending moment at point of contraflexion. So the pressure intensity we know, that is 133.34 into the total distance. What is total distance? Total distance is 2.25 meters. Okay, the total distance is 2.25 meters. So 2.25 square divided by 2. That is WL square by 2. 2.25 square divided by 2. So this is in one section, and we have other loads also, that is load from column 1. So what is the load from column 1? 300 kilonewtons into what is the distance of load that is acting from column 1? It is 1.75 meters. Okay, 1.75 meters at a distance, that is x1 distance. 1.75 is x1 distance, this one. So from this we can calculate the maximum bending moment, which will be minus 187.49 kilonewtons meter. 187.49 kilonewtons meter. Since it's in negative, it's a hogging moment. That is, it should go on the upper side. So that's what 187.49. So that's how we have to draw the shear force and bending moment diagram. So this is all about the shear force and bending moment diagram. Now here we have got how many bending moment values? 3 bending moment values. So which one we have to consider? Among all the 3 bending moment values, we have to consider the maximum one. Whichever is having the maximum one, we have to consider that one to calculate the depth of footing. Now here you might say that 2 are having positive symbols and 1 is having negative symbol. But while deciding the maximum bending moment, you should neglect the symbol, or you should neglect the sign convention. It's not required. You should not consider the sign convention, especially when you're deciding the maximum bending moment. So therefore, okay, therefore, maximum bending moment, the maximum bending moment, that is M max, you can say. Maximum bending moment M max equals to, so what is the maximum bending moment? 16 is one value, 150 and 187. Don't consider this minus symbol. Assume that minus symbol is not there. So therefore, the maximum bending moment is 187.49 kilonewton meter. That's the maximum bending moment value. So from this maximum bending moment value, we have to determine the depth of the footing. Okay, let me write that point. Note note among all the three bending moment values, among all the three above bending moment values, we have to consider the maximum bending moment for calculation of depth of the footing. And the thing is irrespective of sign convention. So neglect the sign convention. Okay. So you should not consider this negative and positive. Within the value only you have to see. Right. So from this, we can calculate the maximum bending moment. So I'm sorry, depth required. So let's find that depth required for footing. Depth required for footing. So how to calculate the depth required for footing? We know the formula, which is mu equals to 0.138 into FCK into B into D square. So from this formula, we can find out the depth required value. So we know the FCK, that is grade of concrete, and the value of B, which is width of the footing, it is limited to 1500 meters or 1500 mm. So maximum moment value we know, which is 187.49. So 187.49 into 10 power 6, that equals to 0.138 into FCK, that is 20, into B, so that is width of the footing is limited to 1500 mm into D square. So from this, you can get the value of the depth of the footing. So once you calculate this equation, the value of D, that is the depth of the footing, D equals to 260.64 mm. So what I'll do is capital D, I'll assume it as, let's say, some 400 or 450, 500, any value you can say. Let's go with 450 mm. We'll check whether it will come good or not. That is in shear and flexion. Right. So from this, we can decide the overall depth of the footing as 450 mm. So depth provided or depth available, you can say depth available or provided equals D provided, PROV. I'll just make it as PROV. So depth provided equals to so I'm just assuming the clear cover as 50 mm, that's for footings. So the overall depth minus clear cover, that is 50 mm, minus the diameter of bars also I'm assuming, which is 16 mm diameter bars, divided by 2. So that equals to 450 minus 300, 300 minus 8. Oh, sorry, 400 minus 8, that is 392 mm. So that's the depth that we have provided. So I'll just write it here. Assume cover as 50 mm and diameter of bar as 16 mm. So that's how we can find out the depth required for footing. So in tomorrow's session, we are going to look into the other calculations. That is, we have to find out the shear, one-way shear, two-way shear, and reinforcement. Reinforcement calculation is the biggest part in this combined footing design, because here you can see, based upon the loads, along this side you have the sagging moments, and here you have the hogging moment, negative moments and positive moments. So you have to be very careful in deciding how many reinforcement bars you have to provide at the bottom of the footing slab or the foundation slab, and how many you should provide at the top of the foundation slab. That I'll explain you very clearly in the next session. So that's from my end for this particular session. If you have any doubts, you can unmute and ask the doubts. Thank you.